What if I told you we can run StarCraft inside the Godot engine? Hey everyone, Juxxec the Balkan Developer here. If you're a StarCraft fan or just interested in game development, you're in the right place. In this series, I'm remaking StarCraft's engine in Godot, from scratch. Using the original assets, I'll replicate its mechanics and systems as accurately as possible. The goal for this first episode is simple, render a StarCraft map inside Godot. But to do that, we first need to understand how StarCraft stores its game data. I used a StarCraft 1.16.1 installation for this video. Now let's jump in. StarCraft doesn't store assets in separate files and folders. Instead, it packs everything into MPQ archives, a format Blizzard developed in the 90s. These archives contain almost all game data: graphics, sounds, scripts, unit stats, and maps. To extract a file, you need to know its exact name. Most MPQs include a list file, which is a catalog of file names, but the main game archives don't. So either get the list file from the community or reverse engineer it. Map files are also MPQs and they do include the list file, so they're easier to work with. Instead of building my own parser, I use Stormlab, a powerful C++ library. It is designed to work with MPQ files and saves me a lot of time, as I won't have to spend time debugging my parser. To use it in Godot, I build a GD extension around it. This way, I can extract files directly inside Godot. Building the extension was not easy. Even with the documentation, it is a very involved process. I ran into multiple compilation and configuration issues. I won't go into too much detail here, as it is quite boring, but it was worth it in the end, as I can now extract files from the MPQ archive as packed byte arrays. With that working, we can start digging into how StarCraft builds its maps. StarCraft uses different tilesets, like Desert, Badlands, Ice, and Jungle, and each tileset is made up of several binary files inside the MPQ archive. To render a map, we need to parse all of the files. StarCraft stores tiles as indexed images, meaning instead of saving each pixel as red, green, blue, and alpha values, it stores a single index referring to a color from a list of colors, the palette. The tilesets are made up of mini tile images that get combined into mega tiles that get grouped together to form terrain types. The WP file holds the color palette, exactly 256 colors. Each color is 4 bytes, 1 byte for each channel. But the alpha channel isn't used in tile rendering, so we can just ignore it. Mini tiles are read by 8 pixels inside. Each pixel uses 1 byte, making each mini tile 64 bytes in size. The mini tiles are stored in the VR4 file. Mega tiles are made from 4x4 mini tiles. They have a size of 32 by 32 pixels. The mini tiles required to construct the mega tiles are stored in the VX4 file. Information about which tiles are walkable, block vision, can be built over are stored in the VF4 file. The CV5 file defines the tile groups, the building blocks used to paint the terrain in the map editor. Each group in the file is defined as a set of mega tiles, 16 per group. I wrote a script that parses all of these files and converts the data to a tileset resource that can be used with a tile map node in Godot. This did not go very smoothly. I had numerous issues with this part. The documentation is a bit lacking in this regard. It is easy to create the tileset with the editor, but doing it via code was a whole different story. But with that working, we can proceed to the next step, reading the map data. Every StarCraft map is just an MPQ archive, and inside it a file called scenario.chk. This file contains everything about the map, the tileset to be used, the map layout, player starting locations, and triggers. It's made up of sections. Each section is represented by a 4-letter code and the size of the data inside the section. For example, the MTXM section holds the tile grid, which tiles from which group to use at each map position. I wrote a script that reads the MTXM section and combines it with the tileset resource to construct the map. The map is stored as a tile map node. I slapped a camera that can be panned around by moving the mouse close to the edges of the screen and started looking around the map. Let us look at what we have generated. Well, that doesn't look quite right. The shape appears to be correct, but the tiles are all wrong. Okay. That's better, but it still isn't correct. There are holes in the map. Why? Comparing it to the map editor, I can see that there are some graphics where the holes are. Those are called doodads. There are a couple of types of doodads, like sprite, unit, and tile doodads. I'm going to focus on the tile doodads for now. Tile doodads are stored in the tile set. Each tile in the tile set has an ID. Doodads have an ID of 1024 and larger. There are some flags in the tileset data that can mark a tile as being a doodad tile. I modified my code to respect the dot tiles. Let us see how the map looks now. Turns out that I was indexing the CV5 groups wrong. After a bit of playing around, I got the map to render correctly, at least at the tile level. Well, that is all I could manage to do in 2 weeks. We will continue this in future videos. Next time, we will start looking into sprites and animations so that we can prepare for units. See ya!